Okay, so welcome to the second video in the discrete structures series. In this video, we're going to be covering sets, different set representations, and we're going to look at different set terminologies. And this includes things like finite sets, infinite sets, and empty set, unit sets, all those things that we need to describe different types of sets. We're going to look at Venn diagrams, and this is a way to represent sets in a graphical manner. And we'll also be looking at a few implications of set theory and a few interesting topics that are a direct outcome of set theory. So first things first, what is a set? In simple terms, a set is simply a collection that has certain properties: uniqueness. Each element in a set has to be unique. I'm not allowed to repeat the elements. Each element has to be unordered. It's not actually about an element, but the order of the elements in a set should not matter. And I'm not allowed to permute the elements and call it a different set, right? So that's not something that I'm allowed to do. And it has to be well defined, in the sense that each element in a set needs to be unambiguous, right? Whether or not it's an element. So for example, if I say a set of intelligent people, there's no distinct line, right? It's a gray area, right? Some people might be considered intelligent by some others and not, and so on. So it's not well defined. But in order to be a set, we want elements to be well defined. So very basic stuff, right? We've been doing this for quite a bit now. In terms of notations, a set is generally denoted with capital letters A, B, C, etc., and so on. Elements in a set, whatever they represent, are generally represented with small letters, right? And it's just a convention, nothing fancy going on around here. And all right, so next thing that we look at is going to be about set representations. So representations of a set. And before we get into this topic, I think a lecture on set theory goes unfinished without a tribute to Georg Cantor, Georg Cantor. And this person was a brilliant mathematician, and he's also attributed to be the inventor of set theory. And there are a couple of pretty interesting things that Cantor came up with, right? And one of them is called the Cantor's paradox. And Cantor's paradox simply ponders upon the concept of set of all sets, right? Or a set containing all sets. So the idea is that this statement is supposed to be paradoxical, right? So if I were to assume there is a set that contains all sets, right? So this is a set, let's say I put a crown over this. It's a power, superpower set that contains all other sets. Then this set itself should also be in this set, right? Because it contains all sets. Now, if I put this set into it, it's no longer the same set, right? It's a new set that I've created. And this new set, again, has to be included, right? And that goes on, and it's not resolvable, right? That doesn't resolve. That's why a set containing all sets cannot exist. Now, if I choose not to include this element, then it is not the set containing all sets, because it does not contain the set containing all sets, so to speak. So it's quite a play of words, but it's also quite interesting. So one more topic that comes from Georg Cantor is the Cantor's set, and it raises really big implications on the sizes of different infinities. Basically, it goes on to show that despite removing infinite items from a set, the size of the resulting set is still the size of the parent set. So we won't go into too much detail about this, but you'll see me doing a few sketches about this. I didn't have time to explain all of this. So you can have a look online if you need to regarding Cantor sets. Okay, getting back to our topic of the representations of a set. So we're going to look at a few different ways we can represent a set. It's quite trivial to speak, but we'll just go through them quickly if we can. So let's say description method is the first one. So this is simply a method where we describe certain properties of a set, and that helps us distinguish what the elements are. So for example, a description method would say, let's say, a set of stars that are bigger than the sun, right? And that would be a descriptive way to define a set. So a set of stars bigger than the sun. So another method to actually describe a set is called tabulation or listing. And this is a method where we directly list the elements of the set, right? Nothing too fancy. If I say 1, 2, 3, 4, maybe to represent the set of natural numbers. So I'm actually listing the elements. Another method is the rule method, or it's called the set builder method. And the set builder method is used to describe a set using some sort of, basically a rule that defines whether or not an element belongs. So let's say I prepare a set of all elements x in natural numbers. Let's say I want x in natural numbers, so that x is divisible by 2, right? And I'm just using the modulo notation here to represent that. But the idea is I just want all the even numbers, right? And this is based on a rule. And if I were to list this, I would actually be listing 2, 4, 6, 8, and this set of even numbers that give me a remainder of 0 when divided by 2. Okay, so that was about set representations. Now let's look at set terminologies. So these are different terms that we use to describe different types of sets, right? So that communication is easier. So we have a finite set. Finite set is the set that has a fixed number of elements. Infinite set, so a set that has an uncountable or infinite number of elements, right? Empty set, so this would actually be represented by a phi, and this would be a set containing no elements at all. So an empty set. We have our unit set, and it's a set that contains exactly one element, right? And this is also called a singleton set. All right, so that's about a unit set. There's one more terminology, maybe universal set. A universal set is kind of a set containing everything in the universe, right? So whatever you could think of is contained in this set. So it is quite useful in doing some set arithmetic. So I could say, everything except A is the universe minus A, right? So some things like that. So it's a useful concept to actually take care of. One more concept, and this is a little bit more useful: power set. So actually, we are already familiar with the concept that a set can contain sets inside of it, right? So a set of sets, so to speak. And a power set is a set that contains all possible subsets of a given set. So let's say I have a set called A, having two members A, B. Let's say I just do 2y3, right? That's going to give me fewer elements in the subset anyway. So I'm going to say that the power set of A is going to be a bigger set, and this set is going to contain all of the possible subsets of A. So it could be the empty set. I could choose to take nothing, and I could choose to take only A. So I'm putting a set in here. I could choose to take a B, and I could choose to take a set that contains A and B. So these are all the possible subsets of this set A. And you would notice that for two elements here, the number of subsets is 4. And if, let's say, I had only one element A, the number of subsets would be 2, right? So empty or just a set containing A. So for one, I have 2 subsets. So for 2 elements, I have 4 subsets. And I could, prove using mathematical induction that a set in general would have 2 to the power n subsets, given that it has n elements, of course, right? So let's say this has 2 elements, so 2 to the power 2 is 4, and that is why this has 4 subsets, right? And it doesn't quite satisfy, just proving it by induction, right? Why 2, right? Why not 3 to the power n? And that has to do with the fact that every element can either belong to the subset or it may not belong to the subset, right? So 2 possibilities, right? So that's where the 2 comes from. And to elaborate that a little bit, let's say I have a set A, B. So how can I form different subsets of this set, right? I could choose to, I could choose A or not choose A. So that gives me 2 possibilities here. I could choose B or not choose B, and that gives me 2 possibilities here. And if I multiply both possibilities, that's 4, right? And that's how we generalize the concept for n number of elements in a set. So that would give us 2 to the power n subsets. And the next thing that we're going to look at are ordered pairs. So this is also quite a useful concept in Cartesian geometry and in so many other disciplines, right, where we need to take a pair of numbers and then perform various operations on them. So an ordered pair is simply a pair of two values, right? And first we say pair. So A, B, a pair, generally denoted with these curly braces. And then when we use this kind of braces, A, B, we call this an ordered pair, right? And when we say ordered, we mean that the first element being first has some significance, right? So I cannot simply swap the elements and call it to be the same pair. So in this pair, B comma A would be the same as this pair, but in case of an ordered pair, this would not be the same, right? And why would someone create rules like this, right? So what's the benefit of doing this? See, it has, these things applies in certain situations in practice, and these things apply in certain other situations in practice. So for example, if I have this geometry, of a Cartesian grid, for example, and I have the point 3 comma 4, and I have another point, this doesn't look like 3 comma 4, does it? This looks like 4 comma 3. And okay, so this is 3 comma 4, and you see that this point is actually distinct and different from this point, right? So if you want to model this kind of universe, you need ordered pairs, right? Because you want the different permutations. I'm sorry, this was supposed to be BA is not equal to be AB. So if we need to model this, we need ordered pair, right? In some other situations, the permutation may not matter and we might choose this model. But okay, these are just constructs that help us build more complicated things. Okay, so the next topic in line is the Cartesian product. And the Cartesian product is simply a set of all ordered pairs that you can form from two given sets. So I have A, I have B. Let's say this set contains A, B. This set contains 1, 2. And in order to, and this is the notation for Cartesian products, by the way, A cross B would be the new set that I can form by taking one element of A and one element of B and making sure I cover everything. So I can take A1, A2, B1, B2, sorry. Okay, so this is my Cartesian product, right? So nothing too fancy of a concept here either, but there's a way to formally define this if you want. So a Cartesian product between two sets A and B would be defined as all ordered pairs A, B, such that A belongs to A and B belongs to B, right? And that way you would compute the Cartesian product of any two given sets. So also quite a trivial concept, and we're gonna look into the next topic. That's gonna be Venn diagrams, and this is gonna be the last topic of the day. So a Venn diagram also pretty simple and pretty trivial. We've been learning about this, since our childhood. So not much to go about here, but you know that it's a graphical way to represent set and elements and the fact that there are intersections and things belong to different regions, right? So let's say for two sets A and B, this is a typical Venn diagram. I'll use my border to construct my universal set. It's a neat trick. Okay, so A, B, and this is the set A, this is the set B. Now see, whatever the members of A and B are, there's always a region where they could belong, right? So anything that belongs here is a member of A as well as B. Anything that belongs here is only a member of A. This one is only a member of B. Here is everything else in the universe, right? Because this outer range is a universe. Now for three sets, I could do the same thing, and I'm doing this for a region. Hold on. So I could draw my universal set around, pardon my bad drawing, but okay, this is the universal set, and I have three sets A, B, and C, and I could see, okay, this represents the intersection between A and C. This represents the intersection between everything. So for three sets, all possible regions are shown by this diagram, right? So I think you know where I'm getting at, right? So what about 4 sets? What if I'm told to draw a Venn diagram for 4 sets A, B, C, and D so that I can show all regions, right? I already have 3 sets here. If I draw the 4th circle somewhere like this, I'm not getting an intersection between A and D, and it seems quite tricky. It is quite tricky, and there is actually a way and a fancy way to do this, and it's called the Edwards diagram, and you draw it this way. So you begin by drawing your primary set A, let's say, and when you draw B, let me try to use a different color if I can. The set B would span right through A, so quite similar. Now for C and D, let me choose, so this makes for a C, and if you consider this big area, I'm going to call it D. All right, so if I look into this diagram, I see that there are, intersection points available for all regions, right? So if I'm looking for intersection between all 4 sets, I think this would be the region where all 4 sets intersect, and you could check, right? All those regions exist. Now if you go beyond 4 sets, it's near close to impossible, at least by drawing regular shapes, right? So you have to draw very irregular polygons and stuff like that. If you want to explore more about this, you can find this stuff online. So yeah, so that's all I would like to really say about Venn diagrams, and that should conclude this video. So see you guys in the next one. Have a good day. Bye.